Overfitting and underfitting are the two terms used in machine learning to describe how well a machine learning model learns and generalizes to new data. They identify the most important causes of poor performance in machine learning models. Overfitting means good performance on the training data and poor generalization to other data. A model is overfitted when it models the training data too well. That is when it learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on a new data. Underfitting means poor performance on the training data and poor generalization to other data. A model is underfitted when it can neither model the training data nor generalize to the new data. Let's see an example of an overfitting model. It performs very well on the training set, so the blue dots, but it performs poorly on the test data, the orange dots. As a note, the R2 score presented here measures the degree of correlation between actual values and predicted values. The closer it is to 1, the better the correlation. Let's see an example of a biased model. It performs poorly on both the training data and the test data. Finally, let's see an example of a good model. It performs fairly well on both the training data and the test set. Both overfitting and underfitting can lead to poor model performance, but by far the most common problem is overfitting. There are a few methods used when dealing with overfitting models. Let's see what we can do to limit overfitting. The most popular resampling technique is k-fold cross-validation. It allows you to train and test your model k times on different subsets of training data and build up an estimate of the performance of a machine learning model on unseen data. A validation dataset is simply a subset of your training data that you hold back from your machine learning algorithm until the very end of your project. After you have selected and tuned your machine learning algorithms on your training dataset, you can evaluate the learned models on the validation dataset to get a final objective idea of how the models might perform on the unseen data. One of the first steps to make when dealing with overfitting is to decrease the complexity of the model by removing layers or reducing the number of neurons in order to make the network smaller. Training with more data, if available, can help algorithms detect the signal better. High dimensionality will increase the computational complexity, increase the risk of overfitting, as your algorithm has more degrees of freedom, and the sparsity of the data will grow. Hence, dimensionality reduction will project the data in a space with less dimension to limit overfitting. Early stopping is another approach to avoid overfitting. It consists in monitoring the performance of the model that is being trained on a separate test dataset and stopping the training procedure once the performance on the test dataset has not improved after a fixed number of training iterations. So here's an example of the best practices. So as you can see in the first diagram, we could see overfitting, but some things you can do is 1, use a simpler model as depicted in the second diagram, and 2, you can use more training data in order to improve the performance.